Hello, everyone. Welcome to our podcast, where we dive deep into the latest research papers in AI and software engineering. Today, we're reviewing a fascinating paper titled A.S.E, a repository-level benchmark for evaluating security in AI-generated code. Are you ready to explore this too?
Absolutely. This paper is quite timely, given the rapid adoption of large language models, or LLMs, in software engineering. The authors point out that while LLMs are great at generating code, there's a growing concern about the security of that code. Did you notice how they emphasize the risks of vulnerabilities in AI-generated code?
Yes, that stood out to me. The paper mentions that existing benchmarks mostly focus on code quality, like syntax correctness and functional accuracy, but often overlook security. That's a big gap, especially since insecure code can lead to data breaches or system failures. So, what's the main contribution of A.S.E?
The A.S.E benchmark is designed to fill that gap. It's a repository-level evaluation benchmark, which means it assesses code generation in the context of entire software repositories, not just isolated snippets. This is important because real-world programming involves understanding the broader context, not just writing a single function.
That's a great point. The authors also highlight that previous security-oriented benchmarks are often based on synthetic code snippets, which don't reflect the complexity of real-world projects. A.S.E, on the other hand, uses data from high-quality GitHub repositories with documented CVEs. That ensures the scenarios are both realistic and security-sensitive.
Exactly. And to make the evaluation even more robust, A.S.E applies semantic and structural mutations to the repositories. This helps prevent data leakage and ensures that the models are being tested on their actual capabilities, not just their ability to memorize training data.
I found the construction process of the benchmark quite thorough. They start by collecting raw CVE data from both public and internal sources. Then filter repositories based on criteria like active maintenance and the presence of documented vulnerabilities. Security experts then review and annotate the code, ensuring that the vulnerabilities are both detectable and reproducible.
Yes, and after that, they expand the dataset by applying semantic and structural mutations. This results in 120 repository-level vulnerability instances, covering 4 common vulnerability types: SQL injection, path traversal, cross-site scripting, and command injection. The dataset also spans 5 programming languages: PHP, Python, Go, JavaScript, and Java.
That's a diverse set of languages and vulnerabilities. It's interesting that PHP makes up 50% of the dataset, reflecting its prevalence in web development and its history of security issues. The inclusion of multiple languages also allows the benchmark to assess how well models generalize across different programming environments.
Another key aspect is how A.S.E sets up the code generation tasks. For each instance, they remove the vulnerable code and ask the LLM to fill in the gap, using both a functional description of the vulnerability and relevant code context from the repository. This simulates how AI assistants like Cursor might be used in real-world development.
Right, and the evaluation doesn't stop at just checking if the code compiles. They use a multi-dimensional assessment, looking at code quality, security, and generation stability. Security is measured by whether the generated patch reduces the number of detected vulnerabilities, using expert-crafted static analysis rules tailored to each CVE.
Stability is an interesting metric as well. It measures how consistently a model produces correct and secure code across repeated runs. This is important because LLMs can sometimes generate different outputs for the same input, which could be problematic in a production environment.
Let's talk about the experiments. The authors evaluated 26 state-of-the-art LLMs, including both proprietary and open-source models. They compared fast-thinking and slow-thinking reasoning modes. What did you think of the results?
The results were quite revealing. None of the models surpassed the 50-point threshold on code security. even though many produce syntactically correct and functional code. This highlights that secure coding remains a significant challenge for current LLMs.
Claude 3.7 Sonnet achieved the highest overall score, but its code security score was still below 47. Interestingly, open-source models like QN3-235B-A22B Instruct performed almost as well as the top proprietary models, especially in terms of security.
That's encouraging for the open-source community. The paper also found that fast-thinking decoding strategies consistently outperform slow-thinking ones for security repairs. This suggests that concise, direct reasoning may be more effective for secure code generation than more elaborate, multi-step approaches.
The analysis also showed that mixture of experts MOE architectures generally outperform dense models in security tasks. This could be an important direction for future model development.
Another interesting finding was that path traversal vulnerabilities were the most challenging for all models. Even the best-performing models struggled with this category, likely because path manipulation requires a deep understanding of file system operations and context.
The authors also examined whether model performance scaled with size. For the Quay-Wen series, larger models generally performed better, especially in overall and quality scores. However, the improvement in security performance eventually plateaued.
They also checked for consistency between the original and mutated datasets. The results were stable, indicating that the benchmark is robust and not affected by data leakage. This is important for ensuring the validity of the evaluation.
The paper concludes by emphasizing the need for more secure and reliable LLMs in software engineering. A.S.E. provides a robust foundation for future research, enabling the community to develop and evaluate models that can generate secure code in real-world scenarios.
They've also made the source code and dataset publicly available, which is great for reproducibility and community engagement. Researchers and practitioners can access the benchmark and evaluation framework to test their own models.
Let's dive a bit deeper into the design philosophy of A.S.E. The authors stress the importance of using real-world, repository-level data sources. This ensures that the benchmark reflects the actual challenges faced by developers in production environments.
Yes, and by simulating real-world AI programming tasks, A.S.E. mimics the workflow of AI assistants. The code generation tasks require models to understand both intra-file and cross-file contexts, which is much more complex than generating isolated code snippets.
The code assessment methods are also noteworthy. Instead of relying on manual or LLM-based judgment, which can be inconsistent, A.S.E. uses targeted static vulnerability detection rules for each test case. This ensures high accuracy and reproducibility.
The construction process is quite rigorous. After collecting and filtering repositories, security experts annotate the vulnerable code regions and design custom detection rules. The dataset is then expanded through semantic and structural mutations, increasing its diversity and robustness.
The benchmark covers 4 major vulnerability types, each mapped to a specific CVE entry. This allows for a focused evaluation of model performance on the most critical security issues in web development.
The inclusion of 5 programming languages also adds to the benchmark's realism. It's important to test models across different languages, as each has its own security challenges and idioms.
The code generation tasks are carefully designed. By masking the vulnerable code and providing relevant context, the benchmark tests the model's ability to reason about the repository as a whole, not just generate local fixes.
The evaluation pipeline is comprehensive. Quality is assessed by whether the patch integrates cleanly and passes static checks. Security is measured by the reduction in detected vulnerabilities, and stability is evaluated based on the consistency of outputs across runs.
The overall score combines these 3 dimensions, with security weighted most heavily. This reflects the primary goal of generating secure code, while also ensuring that the code is correct and stable.
In the experiments, the authors found that even the best models have a long way to go in terms of security. Most models produce correct code, but a significant portion of it remains insecure.
The analysis of reasoning paradigms was particularly interesting. Slow thinking modes, which allocate more computation or multi-step reflection, tended to underperform compared to fast thinking modes. This suggests that more complex reasoning doesn't necessarily lead to better security.
The architectural analysis showed that MoLLE models generally outperform dense models. This could be due to their ability to specialize in different aspects of code generation, including security.
The task-level analysis revealed that path traversal is the most challenging vulnerability type. This highlights the need for models to develop a deeper understanding of file system operations and access control.
The scaling law analysis showed that larger models generally perform better, but the improvement in security eventually plateaus. This suggests that simply increasing model size is not enough. Architectural and training improvements are also needed.
The consistency analysis between original and mutated datasets confirmed the robustness of the benchmark. The model's performance was stable across both versions, indicating that the evaluation is not affected by data leakage.
The paper's conclusion emphasizes the importance of realistic, context-aware evaluation frameworks like A.S.E. By providing a comprehensive and reproducible benchmark, the authors hope to drive the development of more secure and reliable AI-assisted programming tools.
The public release of the source code and dataset is a significant contribution. It enables the community to build on this work and develop better models and evaluation methods.
Let's discuss some of the broader implications of this research. As LLMs become more integrated into software development workflows, ensuring the security of AI-generated code will be critical. Benchmarks like A.S.E. are essential for identifying weaknesses and guiding improvements.
Absolutely. The findings also suggest that prompting strategies and model architectures play a crucial role in secure code generation. It's not just about having a bigger model, how you use it matters just as much.
The narrow gap between open source and proprietary models is encouraging. It means that the broader community can contribute to and benefit from advances in secure code generation.
The focus on repository-level evaluation is also important. Real-world software development involves complex dependencies and context, which snippet-level benchmarks can't capture.
The use of expert-crafted static analysis rules ensures that the evaluation is both accurate and reproducible. This is a significant improvement over manual or LLM-based assessments.
The multidimensional evaluation, combining security, quality, and stability, provides a holistic view of model performance. This is essential for practical adoption in production environments.
The challenges identified in the paper, such as the difficulty of handling path traversal vulnerabilities, point to areas where future research should focus.
The finding that fast-thinking strategies outperform slow-thinking ones for security repairs is intriguing. It suggests that concise, direct reasoning may be more effective for certain tasks.
The architectural advantage of MoLE models indicates that specialization within the model can lead to better performance on complex tasks like secure code generation.
The scaling law analysis shows that while larger models generally perform better, there are diminishing returns. This highlights the need for smarter training and architectural choices.
The robustness of the benchmark, as demonstrated by the consistency between original and mutated datasets, ensures that the evaluation is reliable and free from data leakage.
The public availability of the benchmark and evaluation framework will accelerate progress in this field. Researchers can use A.S.E. to test new models and approaches, driving innovation in secure AI-assisted programming.
In summary, this paper makes a significant contribution by providing a realistic, comprehensive, and reproducible benchmark for evaluating the security of AI